Calculus BC, this is More on Integrals Worksheet 1. This is problem number 3. Here's a little friendly hint on how to do the problem. We've got a graph of acceleration, and you can see this is from 0 to 18 seconds. But we're told that at time 0 we have a starting velocity of positive 55 feet per second. And the car's acceleration is actually a piecewise linear function. You can see sometimes acceleration is positive when we're above the x-axis. Sometimes it's negative in that we're below. And acceleration, of course, will be the y values on this graph. So as we look at letter A, is the velocity of the car increasing at t equals 2 seconds, y or y not? Friendly reminder, we could say f of x is increasing if f prime of x is greater than 0. So for part A, what we're going to really look at is we can say v of t is increasing if v prime of t, which by the way, that's really what a of t is greater than 0. So let's take a look and see what's happening at 2. At 2, we can say a of 2 is equal to 15. The acceleration, this y value, is greater than 0. So for part A, we can answer the question now, is the velocity increasing at t equals 2? We can say yes. Velocity is increasing at t equals 2 because v prime of 2, which is equal to a of 2, is greater than 0. And that would be our answer and our reason, the why or why not. Okay, well, as we begin to wrestle with this, I'm sure kids are going to fall back and they're going to say, now, you know, this whole worksheet is more on integrals. So, of course, we're going to think that we're going to need integrals for many of these problems. Realistically, we could imagine we're going to need them for every problem. And obviously, we're given acceleration here. Maybe we just need to review something. If I were integrating from 2 times, and rather than call it a and b, maybe it's even more helpful to just call it t1 and t2, a beginning time and an ending time. And if I were to integrate the acceleration function, you could wonder, what in the world are we finding? Well, first off, integrals are net area. And we said before that even if you would envision that you had rectangles here, if we had a rectangle, we could say, well, our y value is measured in feet per second squared. Our x value, which happens to be time, would be seconds. So the area, or what we'd be working with, finding net area, of course, positives and negatives can come into play. You might guess that the units that we'd find from an integral would be feet per second. And you could say, now, wait a minute, wouldn't that go in line with velocity? And it would. But look, I want to go back to this integral right here, and FTC means the fundamental theorem of calculus, and that's so incredibly important. It lives up to its name. Fundamental theorem of calculus, that sure sounds important. It unlocks what's happening here, guys. Look, I'm going to take my antiderivative of acceleration, which is velocity, and then I'll plug in my 2 times, finishing this out. So I'd have v of t2 minus v of t1. So what do we get if we integrate from t1 to t2? We're going to get the change in velocity, here's that big word, change. The change in velocity when on that time interval. We can say from a time between t1 and t2. So as we go that number of seconds, this is how our velocity would change. Obviously, your area could be positive, in which case you'd have a positive change. Your velocity would increase. Your area could be negative just as well, in which case your velocity would be decreasing. But as we're reading ahead, you can begin to, just take what we just talked about as a great summary. They're saying at what time other than 0 and 18 seconds, at what time in that interval is the velocity of the car 55 seconds? At what time other than t equals 0 is the velocity there, and why? Well, my goodness, as we think about it, let's just look right here. If we were to integrate, if we were to just integrate here, and why am I picking that? I hope you can see we could pick that because that's a trapezoid. Look at this. If I just went from 0 to 6 of a of t, I could find that. Now, what's the area of a trapezoid? The area of a trapezoid, you might remember in geometry, 1/2 base 1 plus base 2 times the height. Well, we could say here's 1/2. Well, what's your base 1? Remember, your bases are your parallel sides. Well, how big is this the horizontal segment going from t equals 0 to t equals 2? That's a 2. What are we getting at? This is a 2 right here. How about down below? That's going from 0 to 6. That's going to be a 6. How tall is this? Well, that's a y value of 15. We could very, very quickly say this is 1/2 times 8 times 15. 2 goes into 8 4 times. 4 times 15 is 60. This is 60 feet per second. Guys, this shows a positive acceleration. That means velocity is increasing, like we were just talking about. How much has it increased by? Well, it's increased by 60 feet per second. It started at 55 feet per second. So now it gets that much bigger. You'd say, wow, 55 plus 60. Well, we could see that's 115 feet per second. So we could very quickly say, hey, that's what v of 6 is. This was your change in velocity. You increased by 60. You start right here at the 55 feet per second. That's this thing right here. This is your start. So you have your start, you've got your change. So you could say, wow, look at that. Well, the next question is, the question at hand is really, is there a time when the velocity of the car goes back to 55 feet per second? The change that we just saw was an increase of 60 feet per second. Could we ever decrease 60 feet per second? Could we, in fact, cancel out the gain that we just made? And take a look at this. Here's another trapezoid. Look at this. This would be a base of 6 from 6 to 12. And if I drop this down here at 12, look at that, from 10 to 12, that's a base of 2. And this is negative 15. Oh my goodness. Look, you have a congruent trapezoid. You have a congruent trapezoid. You've got a base of 12. A base of 6, so sorry. And a base of 2 and a height really of negative 15. What are we really getting at? I'll tell you what, guys. This thing right here, we could say in a heartbeat is going to be negative 60 feet per second. That's where acceleration is negative. All these y values are negative. So in other words, what we're really seeing is this. The gain of 60 feet per second up to time 6 would be canceled out with a decrease of 60 feet per second. In other words, what we're really seeing for part B is that the integral from 0 to 12 of a of t dt is 0. So what that's representing is the change in velocity. We could say, so v of t has 0 change from that time interval from 0 to 12. V of 0 is equal to 55 feet per second. So in other words, at V of 12, we're back at 55 feet per second. We increased, we decreased the same amount. This right here, this integral equaling 0 is telling us that our change is in fact 0. So let's take a look at C and say, what is the car's absolute maximum velocity? And at what time does it occur? Well, guys, as we look here, we're on a closed interval. And closed intervals, I'll tell you what, that means we need the extreme value theorem. We need the extreme value theorem. So I'll tell you what, you got to check endpoints. That's what it really means. Now, of course, you could, if you wanted to, look at this graph, as if it was v prime of t. And you're always looking for maximums and minimums, and you could say, where is that derivative of v going to equal 0? Where could that derivative of v be undefined? Well, clearly it's here. You can see I'm making a big blue dot at 6. I'm making a big blue dot over here at 16. And we could pretty much, as we look this thing over, here's 6 and here's 16. And you can come over here to 18. And ironically, normally we wouldn't even make a number line here. But we could see that v prime, which is really a, you could see all around here, these are positive values. That means that v is going to increase. It's going to get bigger. And then from 6 to 16, well, that's where, look at all these accelerations right here. That's negative. That means your velocity decreases. And then finally, from 6 to 18, that's going to be positive again. It's going to increase. So, guys, what we're really looking at from this point on is we're checking this out. We can see more or less that we would have a relative maximum at t equals 6. We can see that really quickly. We got a relative max at t equals 6. You could say, well, why is that? Well, that's because v prime, or a, changes from positive to negative. And at 16, we've got a relative min. We've got a relative min at t equals 16. Why? Because v prime changes from negative to positive. Well, we're looking for the absolute maximum, so we know that we don't even have to check 16 per se. I mean, we can certainly still do that, but we know that that's going to actually be a minimum. By the way, we already know what v of 6 is. V of 6, we saw from previous work, was 115 feet per second. That's a relative maximum. What was v of 0? Well, v of 0, look right here at the top of the page here. It was 55 feet per second. They told us that. We just need to check one more thing. We need to check what v of 18 is. And v of 18, well, my word, we could actually figure this out geometrically, and I think that would be smart. We're going to do that in our next video.